So once again, just with adding, it's just simply the adding. Here to find the magnitude, it's first do what's inside for magnitude. And then think about, and if you need to, plot it out. 12 over and 1 up for that vector. Out here to 12 and then up 1. And then magnitude is the length of the hypotenuse of that triangle that it creates. All right. And then in other forms, when we talk magnitude, magnitude with vectors, when we're talking about force vectors, that's how many actually like newtons of force there are. So the magnitude of the vector is the, how many pounds we're pulling with, or something along those lines. It's positive. And then here, we have the same two vectors, W and T, but now we're going to find the dot product. And this one I'm assuming a lot of people don't have right off the top of their heads memorized in terms of how to do dot product. So dot product of two vectors component-wise is you take the X components and multiply them, and then the Y components and multiply them, and then you add the two together. So in our case here, for these two vectors, it would be, -2 times -7 plus 3 times 1. So it'd be 14 plus 3, or 17. So the dot product of those two will just give me a number. The dot product can also be done what we would call geometrically. What does that mean? That means the magnitude of one times the magnitude of the other times the cosine of the angle between the two vectors. And the angle between the two would be if they were both, so if we go back to thinking about a plot here for a second. And now we're going to plot it like this. 1, 2, 3, 4, 5, 6, 7. -7 up 1. This would be vector, was that T? And then W was -2 and then up 3. Did I write that wrong? A -1. I'm like, something's not right there for my last equation. And I didn't copy it down the right way. There we go. It's 7, -1. So that vector would be to the right 7. 1, 2, 3, 4, 5, 6, 7, down 1. That's vector T. Vector W is -3 up 2, or -2 up 3, sorry. That's vector W. Theta is this angle here, the angle between the two vectors. So in a case like this, if I were given two vectors in component form, and if I were asked to find the angle between them, what I would do is I'd start by finding the dot product. That's 17. So that means if I take it in the geometric form here, I know that 17 will equal, so that's going to be T, magnitude of T times the magnitude of W times cosine of theta. Magnitude of W is a right triangle with side lengths 2 and 3. So the magnitude of W would be the square root of 9 plus 4. 3 squared plus 2 squared. So 9 plus 4, which is 13. And then the magnitude of T, this is also a right triangle, length 7 and 1. So 49 plus 1, Again, a squared plus b squared, it's a right triangle. So this would be square root of 50. All this equals 17. And then you run to your calculators and say, well, what is, times cosine theta. So cosine theta will equal 17 divided by the square root of 50, and then also divided by the square root of 13. So 17 divided by 50 square rooted is that number. Divided by 13 square rooted is that number. That is 0.6668. And if I do inverse cosine, I'll find that theta equals 48 degrees, but I can look at that already and I know that that's not right. Because 48 degrees, that is way more than it's over 90 degrees. Remember, cosine is positive in the first quadrant and third quadrant. No, did I do something wrong? It's possible I did something wrong in my calculations. I should get a value that's in my second quadrant.
I think 17 should be negative 11 because 17. I think.
Oh, because I changed yeah, you're right. Because I changed this up here afterwards. So that's a positive 7. So that's 14. This should be negative what?
11.
Negative 11. So that changes my answer down here to negative 11. So this will be a negative number, whatever I get, and it's not going to be this number. There we go. So switching those around, because I'd originally had that incorrectly with a positive and that with a negative. So this would be positive 14, and this would be minus 3. And maybe I did it wrong again here too, but this will be a positive 14. Negative 14, and this will be a negative 3. Should be 7, still be negative 17. I just had the wrong number, so it should be negative 17, not the 11, as I make more and more mistakes. If you can hear from the sound of my voice, I've been sick for several days. So keeping a healthy distance from me is a good idea. But as you know, I rush through things anyway. So this still should have been negative 17. So the number I had here originally is the right number, the negative 0.6667. Negative inverse cosine, 131.8 degrees. Apologize for all the mistakes that were going on in there, but follow through, procedurally accurate, even though I can't multiply or add at this point in time in my life. To find out and you'd use that process for finding the angle between the two vectors. And the reason why is since they have component form, it's quicker to find the dot product for the components. And then I can work it backwards to find the angle between the two. If you remember from exam 2, I believe, that was finding work. Work is a dot product. Work is the dot product of force vector times distance vector times cosine of the angle between them, which I didn't leave space for on the right-hand side. So if you know the force and you know the angle between them and you know how far it's going to go, it's just a matter of multiplying those three things together. If you don't know the angle between them, it's usually going to be something in a picture. Again, like we had on that second exam, where I think the ramp was up 10 degrees and the force vector was up 25 degrees. Well, that means the angle between them was 15, just because subtraction there, 25 minus the 10, I believe is how that was on the exam. So force, let me rewrite it this way. Work is equal to force vector magnitude times distance vector magnitude times cosine of the angle between them. For dot products. Excuse me. Now we move on to new. Last new thing of the semester. So here I have an equation given as y equals x squared minus 2x minus 3, and here's the graph of it. All right. So we're going to kind of develop this conceptually through an example problem. So it's nothing specific or fun necessarily about this particular equation. But what we're going to do is we're going to pick a point and we're going to try to find the slope of a line that goes through a point tangent at that point. So what do I mean? I'm going to take this point right here. And that point we can see is -2, comma, sorry, it's +2, comma, -3. And if I were to try to sketch the tangent line at that point, it's going to look something about like that. It's a line that goes and touches that graph just at that one small itty bitty point and at that one point only. And that'll be what's called my tangent line. Now, to get my tangent line, there's a lot of ways I could go about doing it. I could take, say, if I go to the point to the left of it, right, here, at 1, I go to the point at 3. If I find this, oh, that's going to be a terrible line. If I find the slope of that line, right, it's going to be close. Not exactly, but if I find that, so what would the slope of that line be? Well, slope is rise over run. Or in this case, usually, right, we do y2 minus y1 over x2 minus x1. So the slope of that yellow line would be y2, which is 0, minus y1, which is -4. And you're wondering, where am I getting that from? Right here, the y coordinate is 0. Here, the y coordinate is -4. Divided by x2, which is 3, minus x1, which is 1, which will be then 4 over 2, which is 2. So the slope of that yellow line is 2. Is that going to be the slope of this line? Probably not, but it's going to be close because it looks like, based on my rough drawing, which is not great. Then, well, what if I can pick a point that's closer here and closer here? I could keep doing that and keep working my way closer and closer and closer. Or another process I could use is I could take this point right here, which we said is 2, -3, and compare that with this point up here, which was 3, 0. And the slope of between those 2 points would be rise. The rise is 3. The run is 1. So the slope of that equation, if I'd connect those 2 points, would have a slope of 3. But then what I want you to imagine is if I could take this point and slide it down along my graph to another place, like right there, at about 2.5. I'm over about 2.5 and come down. And what I'll do is I'll go was x squared minus and get a cleaner looking slide. So if I take the point that I'm looking to go through again, right here, which is 2, -3, and pick a point that's a little bit closer, and find that line, connect these points, and find the slope of that line. And then pick a point a little bit closer, here, draw that line, and find the slope of that line. And then if I could, zoom in a whole lot closer. I'm going to make these dots a whole lot smaller. Pick a point, this one point that I'm going through, and this point right there, with just a very, very, very small difference between the two x's. because I say between the x's, this point here, if I take this all the way up, it's going to be 2, because this point here is 2. This point right there is going to be 2 plus some little value. And the letter we're going to typically use is h. So 2 plus h. So over here we had 2 plus some h, but the h was a little bit bigger. Well, what's the y component right there? Well, if the x component is 2 plus h, the y component is f of 2 plus h. And the y component here is f of 2 plus h. It's f of x. Right? Because here, this is f of 2. And that original equation, 2x minus 3. All right, so if I put 2 into that equation, it yields us an answer of negative 3. So this is 2, negative 3. That point is 2 plus h, and f of 2 plus h. This is 2 plus h. This one's f of 2 plus h. Whatever that h is, and my h is getting smaller and smaller and smaller, because the closer they get to each other, so then, let's think of this too. So what's my slope going to be? Slope is going to be y2 minus y1. So my y2 between these 2 points, and by these 2 points, I'm going to take this point and this point. My y2 is f of 2 plus h. My y2 is f of 2. My x2 minus my x1, my x2 is this value, 2 plus h, minus this x value, which is 2. So my slope becomes f of 2 plus h minus f of 2 over h. And then what I can actually do is I can solve that, which we're going to do here next. All right. F of x was x squared, make sure I write it, minus 2x minus 3. I need to find f of x plus h. Well, that will be x plus h squared minus 2 times x plus h minus 3. X squared plus 2xh plus h squared. That's that first thing in parentheses squared out and simplified with FOIL. Then I'll have minus 2x minus 2h minus 3. Which will be x squared. Let's see. Minus 2x minus 2xh minus 2h plus h squared minus 3. There's nothing there that simplifies. I thought there could be. But that's in the numerator. What else is in the numerator for my slope? All right, because I said my slope was f of x plus h minus f of x over x minus h, or in my case, it would be f of x plus h, which is this, minus f of x. So minus, up here's the f of x function, minus x squared. It's minus a minus, so it's going to be plus 2x. Minus a minus, so it'll be plus 3. And this will all be over x minus h. All right. X squared minus x squared. Negative 2x and positive 2x. Negative 3 and positive 3. And I have negative 2xh minus 2h plus h squared. Oh, let's fix this. This up here. I forgot something from my previous slide. It was x2, which was x plus h, minus x1, which was h, or just x. So my x2 was x plus h, my x1 was x. x2 minus, the x is subtracted, leaving just h in the denominator. So this down here is just h in my denominator. So this is over h. This is over h. This is over h. H is reduce. This is negative 2x minus 2 plus h. Now I'm going to fix something else. These are pluses. See, this was a 2xh. I wrote it there wrong. That's a plus. That 2x I moved. H squared. So 2xh. This should have been positive. There we go. That's right. And then you say, well, what was h? We kept trying to get an h, so the difference between the 2 points, so that h was getting smaller and smaller and smaller. So that back to here, what does that mean? The limit as h approaches 0 of 2x minus 2 plus h. Well, as h approaches 0, what does h become in my equation? 0. So this equals 2x minus 2. Here, if this was, so my point was 2 comma negative 3. This point here, which was x plus h comma f of x plus h. And we kept sliding it down this line closer and closer. What I was doing is I was finding the limit as h approaches 0 of f of x plus h minus f of x, y2 minus y1, over x2 minus x1, which we found was equal to the limit as h approaches 0 of f of x plus h minus f of x. The x is up there, subtracted, and we just have over h in the denominator. That right there is the formula for the slope of a line that goes through a point x comma y. Which means this equals, in our case, 2x minus 2. And if I'm looking at this point, what is that? Well, 2 is my x. So I take this and plug it into that equation, and I get 4 minus 2, which was 2. Lucky, that was close to that estimate of the first 2 points I picked. Will it always be that way? No. But this is the slope of the line that goes through that point that is tangent to my original line. So now we're just going to go from quick introduction to thick of it. Find the slope of the tangent at t equals 2. So here's an equation, and we've done equations like this. A ball is thrown vertically with a velocity of 24 meter, this would be feet per second, from the top of a 15-foot building. Find the slope of the tangent line at t equals 2. So to do this, it's going to get ugly for a while, but that's okay. Keep track of all my positives and negatives like we always do. But what we need to do is we need to find the limit as h approaches 0 of f of x plus h minus f of x all over h. So the first thing I'm going to do is I'm going to find, in this case it's h, I'm going to find h of, we could do, I mean technically my variable here is t. You could call it t, you could convert it and just say x plus h if you like working with h's, or x's I mean. So this will be negative 16 times x plus h squared plus 24 times x plus h plus 15. So it'll be negative 16 times x squared plus 2xh plus h squared plus, I'll go ahead and distribute it, 24x plus 24h plus 15. Or negative 16x squared minus 32xh plus, minus 16h squared plus 24x plus 24h plus 15. If I look in there, this is x squareds, xh's, x's, h's. There's nothing in here that can be combined. But that's my f of x plus h. So I will have the limit as h approaches 0 of all of that mess (32xh minus 16h squared plus 24x minus 24h plus 15). And then I'm going to subtract f of x. So it's minus a negative, so positive 16. I know it's t, but we made them into x's, and we're okay with that for now, x squared. Minus 24x minus 15. Oh, and the whole thing is all over h. 15, negative 15. Negative 24x, positive 24x. Positive 16x squared, negative 16x squared. The limit as h approaches 0 of negative 32x h over h minus 16h squared over h minus 24h over h equals the limit as h approaches 0 of negative 32x minus 24 minus 16h. Is there a reason why I flip-flop those two? Yes, because as h approaches 0, 16 times 0 is 0, leaving me only with Actually, I don't even have to have the limit anymore. Leaves me with negative 32, technically t, because it was x's, but we just converted, minus 24. Minus should be plus. You know, see, there it is again. There's my plus. I made it a minus down here. Plus, plus. Keeping track of those. So at t equals 2, it will be negative 64 plus 24, which is negative 40. That would be the slope of the line tangent to this graph at time equals 2. Why is that significant, you say? Well, if you think about a graph, we're going to have a parabola, but this on my x-axis is time. My y-axis is my height. So my units here are seconds. My units here are feet. So slope is rise, so it's feet. My run is time, which is seconds. So my slope, the measurement of slope is feet per second. This is the height function. The slope at a given point is what's called the instantaneous velocity. So this ball or whatever I'm throwing vertically at 24 feet per second, when it's at 2 seconds, negative means it's coming down. And at that moment, the ball is traveling 40 feet per second. And that would be the slope of the line tangent to this function at time equals 2. But the slope itself, its units are feet per second. So at time 2, I can find the height. Plug in 2 and stick it in there and see what the height is. Take this limit, which is called the derivative. It'll find the slope at that particular point, and that would be the instantaneous velocity of the ball at that particular point. So you know both its height, direction, because it's negative. Negative velocity means it's coming down. And then how fast the ball is actually going at that point in time. But this right here, what we just did to find the slope of a line, tangent line at a given point to any polynomial, this is what's called the definition of a derivative. So for those of you that are jumping into calculus next, you'll get to here pretty quickly in the class, but that's what you're doing. They won't teach it to you right away, and I sometimes venture I shouldn't do it either. Plus, but I'm going to do it anyways. So my height function was, I don't need that extra parenthesis in there, negative 16 t squared, 24t plus 15. There is a shortcut to finding the derivative. That's how I knew every time I did it. I'm like, oop, I forgot a negative somewhere. What was my y equals equation? That was y equals, or f of x equals. It was x squared minus 2x minus 3, I think is what we had in the other equation. The derivative, which would be written like this, f prime of x, was 2x minus 2. The derivative of what we had over here, which is h prime of t, was negative 32t plus 24. When you're looking at those equations, do you see anything that's going on that might be a connection from going first one to the second one so quickly like that?
The second term's number stays the same?
The second term's number stays the same. Yep. And negative 16 becomes negative 32. 1 becomes positive 2. So if you think you have an idea, I'm just going to throw out just a random equation up here. Call it f of x equals 3x to the third minus 2x squared plus 4x minus 2. The first derivative of that equation would be 9x squared minus 4x plus 4. Do you see what's happening? Now, if I had to do this, I would actually have to take this x and replace it with x plus h, cube it, multiply it by 3, square it here, multiply it by -2, multiply it by 4, and then subtract the original equation from it, and then all divided by h, because that is the method. Limit as h approaches 0 of f of x plus h minus f of x all over h, because that's the slope. That'll be the slope of the point. This would be a lot of work. But what I did is I took the value of my exponent, multiplied it by the coefficient, and that's my new coefficient, and reduced the power by 1. Take the exponent times the coefficient, so -2 times 2 is -4, and then reduce the power by 1. Take the power of the coefficient, or the power here, multiply it by the coefficient, 1 times 4, which is 4, and then reduce the power by 1. X to the 0 becomes just 1. So the derivative is going to be just a reduction in 1 for every one of your variables. And then the new coefficient was the previous coefficient times the exponent. Will that always be true for polynomials like this? Yes. There's other things that you'll get to. You'll say, if f of x equals e to the x, the derivative of f of x is e to the x, which means the second derivative, that's double prime, is also going to be e to the x. It's just a fun fact about the Euler's constant as a function, is the function is its derivative and is also its second derivative. Lots of fun stuff there. But that's way beyond where we're going to be. I mean, that's halfway through, 3/4 of the way through first semester calculus. But anyways.